Thanks. Perfect. I'll begin with a word of prayer. So, Heavenly Father, we thank you again for this opportunity we have just to meet together and study your creation. I just pray you'd bless this time we have together. I just pray the students would ask good questions as they think of them. And I just pray that you'd use this time, Lord, for your glory, Lord. In your name I pray. Amen. So, before I do any new material, I'd just like to ask you guys for a second, is there anything you have a question about from what we did yesterday or the homework or anything? All right. Well, you can ask me again after we take a break. I'll ask again. So I want to show you now for the next little bit is the method of, well, it's not really a method, but substitutions. And so basically the idea here is to take a given differential equation and make some substitutions so that we can bring it back to something we already know how to do. And again, this is one of the many reasons I say this course is a lot like Calculus 2, right? Because what do we do in Calculus 2? So much of what we do. It's like, how can you take this given integral and make it go back to what? Like a U substitution, right? Like so often, something like that. So it's kind of the same idea. Here, example 1, which is, by the way, 2.42 in my notes at the moment. Dy dx equal to x plus y minus 6 quantity squared. All right. So first of all, it's not linear, so the integrating factor method's out, right? You can't separate variables because that x plus y doesn't allow us to factor either x or y out, right? So like it's not exact either. You can check, but it's not exact. So all three of our methods from last time are not working. So what we do is try something new. And that something new is just to call this thing v. So v equals to x plus y minus 6. All right. So what we're going to do is we're going to replace x and y with x and v. So to do that, we have to do two things. We have to, just replace the variable algebraically where it appears, but we also have to trade dy dx for like dv dx. So to figure out what that looks like, we just differentiate this implicitly, right? So here we have dv dx equals to, what's the derivative of x with respect to x? Well, it's 1, right? What's the derivative of y with respect to x? Well, it's dy dx. So that's, and 6 differentiates to 0, right? All right, great. So in view of these two identities, right? Just like when we do an integration, we have to do what? We have to substitute the integrand and also change the measure, right? Both things are important, same thing here. But if we solve for dy dx, what do we get? dv dx minus 1, right? Equals to what? That's v squared, right? So this gives us that dv dx is equal to 1 plus v squared, right? And that's much better because now we can do separation of variables, right? So separate variables, what do we get? We get dv over 1 plus v squared equals to dx. And so then we do what? I mean, now we can integrate both sides, right? You guys remember the integral of 1 over 1 plus v squared is what? I'll do the easy part. X plus a constant. Aha, there. How about the left-hand side? What's that? Inverse tangent, right, of what? V, right? Yeah. So inverse tangent of v is equal to x plus c. Now, our goal is not to find v, a relation between v and x, right? We want to find how y and x are related, right? Either we want to find an implicit solution or an explicit solution here. So this says that v, right, is the tangent of x plus c, right? And what was v? V was what? It was x plus y minus 6, right? So therefore, y is equal to 6 minus x plus the tangent of x plus c. There you go. Now, all these substitution problems I'm about to show you, they're more or less just like what I just did. all right? You have to choose some substitution that you're going to chase out. You have to understand how the derivative of the substitution works and to replace both dy dx and the expression which defines the differential equation. Let's look at another example. Dy dx equals to, and you know, our goal here is to solve. I'm sorry if I don't always say that, but that's our goal, solve this. So this one, a little bit trickier. So the standard thing to do is to divide the top and the bottom by x to make this look like 1 plus y over x over y over x minus 1. All right. So if you can get dy dx equal to some function of y over x like this, and I suppose possibly you could also have a function. You have an x dependence too, I think. I'm not sure about that. Let me scratch that. Definitely, if it's just got a y over x dependence, if you can like rewrite the differential equation in this form, then this is said to be homogeneous. First order ODE. So these will all be solvable by the method I'm about to show you. Now, I should also caution, like this is standard terminology to call this a homogeneous differential equation. And there are reasons for that in terms of symmetries of differential equations, but we also use this term homogeneous in a very different way starting tomorrow. So just beware, some words are used more than one way. This is one of those. This is the uncommon use of the term, but just to give these a label, this is a homogeneous one. So here we make the substitution, v equals to y over x, all right? Now, we could either differentiate that directly, that'd be kind of, but I find, rather than differentiating this directly, like what I like to do is to say, okay, so y is equal to x times v, right? Algebraically, same substitution. Now, if I differentiate that, it's easier for me to see how dy dx and dv dx relate, right? Because this gives me what? This gives me dy dx is equal to product rule, right? Which is what? It's v plus x dv dx, yeah? So now I can I can go back up here and take this, right, and replace it with that. And this gives me v plus x dv dx is equal to 1 plus v over v minus 1, yeah? At this point, you might say, well, how is that better? Like, I don't know how to solve that either. All right, fair enough. Well, we had to do some work. So this is x. This may bring up some unpleasant memories for you. I don't know. We're going to be facing an integral of a rational function before too long. You know what that means? Well, it might mean partial fractions. I'm not sure. We'll see what happens. But so, all right. This is going to be nicer if we can rewrite it as a fraction. So we make a common denominator there, right? How to rewrite this as a single fraction? This is what? 1 plus v minus v times v minus 1, all divided by v minus 1. Am I right? Can we clean that up a little bit? Let's see here. So we get what is it? 1 looks like plus 2v, right? Plus v squared. I'm sorry, plus v squared? No. Minus v squared, right? All divided by what? V minus 1. It's convenient to rewrite this fraction, for me at least, as the following. This is v squared minus 2v minus 1 divided by 1 minus v. All right, so now we're off to the races. If you look at this and this, we can do separation of variables now, right? I mean, we could before too, but now it's relatively pretty to do the algebra. So what I have here is I have 1 minus v over v squared minus 2v minus 1 dv is equal to what? It's equal to dx over x, yeah? So what I did was you see how I did that? I just multiplied by the reciprocal of the fraction to bring it to the other side. The dx goes upstairs, the x goes downstairs when I bring them to the other side, right? Just doing algebra, treating dx and dv as if they're little infinitesimal objects. Obeying the ordinary rules of algebra. And now we have to integrate. You know, if I differentiate the bottom with respect to v, what do I get? I get 2v minus 2, right? I think a substitution, you can make basically a u substitution here, right? Like if I make this u, then what's du dv? It's 2v minus 2, right? Which is 2 times v minus 1. So if you'll forgive me this small manga-style calculation here, I'll put this over here and work over here instead because, well, you know, I'm running out of board. So with that substitution, this is really, what is it? It's minus 1/2, looks to me like minus 1/2. See, this is, I can get v minus 1 times dv is equal to du over 2, but the minus is off, yeah? So I minus 1/2 du over u, I think, yeah? By the way, guys, I will make mistakes, so it's really important that if you see me make a mistake and you're confident about it, or even if you're just not, if you're half sure about it, interrupt me before I go 3 more minutes and regret my life. It will happen. I do make mistakes. I promise. They will all be on purpose. So if you don't say anything about them, I know that you're, you know, just pretending to be here. Minus 1/2 natural log, the absolute value of u, but u is what? Oh, yeah. That's minus 1/2 natural log, the absolute value of, golly, v squared minus 2v minus 1. Okay, that's going to be equal to the natural log of the absolute value of x plus a constant, right? And so this, great. I mean, now we just have to unsubstitute our substitutions, so to speak, right? So what was v? V was y over x. So going back, I get minus 1/2 natural log absolute value of y over x quantity squared minus 2 times y over x minus 1 close absolute value equal to natural log absolute value of x plus a constant. So there's an implicit solution. I mean, if you're a glutton for punishment, you probably could find an explicit solution here, but I'm not inclined at the moment to do that. All right? Now, this is actually example 2.43 in my notes. But I would say example 2.43 in my notes is wrong. So you will not find this solution in the notes if I recall correctly. I have an error there. I make a sign error early on. It actually makes the integration turn out differently if I recall correctly. I'm going to project in just a minute or two. We'll look at it when I put the projector out. Okay, remind me to take a look at this when we get the projector out here shortly. Example 3 for you guys. like the general spirit of the derivation in the notes is right, but there's like an arithmetic mistake early on which changes the nature of the integration. The technique is still pretty much the same. Example 3. This is known as a Bernoulli differential equation. Bernoulli. And here's, it's sort of almost linear. Y prime plus xy equals to xy cubed. Now, this is my example 2.45. All right. Now, so you see why I say it's almost linear? Like, it would be just straight linear if it wasn't for this, right? If not for this, we would just have a linear differential equation. We would use the integrating factor technique. We'd be done, right? But this is not welcome. But here's the thing. If you divide by y cubed, this gives us like y to the minus 3, y prime plus x, y to the minus 2, I suppose, is equal to x, yeah? And you start to see something that resembles some sort of derivative of y or something. So I don't have a very convincing derivation for why this works in general or anything. It's not really my biggest goal in this course to exposit the Bernoulli problem in general or anything like that. But what we do is we let z equals to 1 over y squared. That turns out to make things nice here. So like, just as a sidebar, if we had dy dx plus p times y is equal to q y to the n power, then you let z equal to 1 over y to the n minus 1. So like that is what we're doing here. This is n equals 3 for Bernoulli. And so this substitution is going to work for us. If you instead had a 4, you would end up needing to make a 1 over y cubed substitution. All right. Now, given the shortness of the summer term, this is the sort of thing I would actually tell you on the test. Substitution problems, I'm probably going to, it's either going to be a bonus problem or it would be something where I would suggest the substitution. You just have to work out the calculus of it, right? I find students have sufficient difficulty, like even after I start the problem and tell you, hey, let v equals y over x to solve the problem, it's still pretty challenging to do these. So I think adding the extra layer of difficulty of choosing the substitution is just a little bit too far, especially in the summer term. But on the other hand, I give you a page of notes, so I'm probably wrong. I should probably make you do it, but oh well, too late. I said what I said. All right, so, but suggesting the substitution and solving the problem, there's still a lot of work to do, right? After I tell you let z equal 1 over y squared, it's not done, right? You got lots to do. Okay, so that means, let's see here. So if z is equal to 1 over y squared, that means z is equal to y to the minus 2, right? So therefore, dz dx is what? Minus 2 y to the minus 3 dy dx, right? Now, is this present anywhere up in here? This is why the substitution's smart, is because letting this be that makes this term appear, which is present there, right? It's not directly that term. There's this minus 1/2, right? So you need to do a little bit of algebra here. Minus 1/2 dz dx is equal to what? It's equal to y to the minus 3 dy dx. The prime notation, of course, is dangerous. It's easy to miss a prime. You have to be really careful with prime notation, right? So I almost kind of prefer dy dx because it's really hard to drop a dx like that, right? It's very easy to drop a prime. It's much harder to drop a dy dx, but on the other hand, it's more writing. So I don't know. Pros and cons, I suppose. All right. So this, we just earned the right to make the substitution, what? So that's really minus 1 over 2 dz dx. So I'm taking this, right? Star becomes minus 1 over 2 dz dx plus what? X. What's y to the minus 2? Oh, right, this is z. That's the thing. Equal to x. Well, what do you, now that is pretty awesome because now we have, let me rewrite it one more step here. dz dx is equal to, oops, sorry, not equal to, dz dx minus 2xz is equal to minus 2x. At this point, we're back to yesterday. Who says you can't travel in time, right? There you go. The whole day back. That is what kind of problem? How should we solve this? I mean, identify that P is equal to minus 2x and Q is equal to minus 2x. Identifying Q doesn't really matter much, but I mean, that's a linear first order differential equation, right? So what technique do we use? Integrating factor technique, right? So what's our integrating factor? Exponential of the integral of minus 2x dx, which is what? That would be e to the minus x squared. So then what's our next move? We multiply the differential equation by integrating factor, right? So we get e to the minus x squared dz dx minus 2x e to the minus x squared z equals to minus 2x e to the minus x squared. So that was multiplying star star by I. Here's star star. Now, what did I tell you yesterday? If we do the integrating factor correctly, what will happen? What has to happen, we have to be able to see a product rule in reverse if we did it right, right? Can you see the product rule in reverse here? This is d dx of what? Are you guys still worn down from the finals in the spring? Like, what's going on? Oh, you're up late watching basketball? I mean, I don't know. So apparently this Kevin Durant guy is like good or something. It's interesting to watch the commentary before the game. Like, they're all talking like the Cavs are going to win because it's just, it has to happen or something. Like the newscasters were so pro the team with LeBron James, that one, whatever that one is. It's very, very biased, the coverage. Like, I don't know. It's funny. I pretty much only watch sporting events when they're the one that ends the season. Like, I'll watch a Super Bowl. I might watch the final game in the NBA. I haven't brought myself to watch the Stanley Cup yet. It's still just boring. I'm sorry. Just people skating around. There was more fighting, you know? I don't know, maybe. So what does this go here? E to the negative x squared z. Thank you. Put me out of my misery. Much appreciated. So it worked, right? Now we integrate both sides. And the beautiful thing here is that the integral of the right-hand side is what? This is, you can just make a u equals minus x squared substitution, right? So when you integrate this, we just get e to the minus x squared if you look at it, plus a constant, right? If you don't believe me, differentiate e to the minus 2x, e to the minus x squared. What do you get? You get minus 2x e to the minus x squared by the chain rule, which is what we have up here. So this is the antiderivative of that. Make a u equals minus x squared substitution if you don't believe me. At this point, we're done. Well, almost done. This gives me z equals to 1 plus c e to the x squared, right? What was z? It's been so long ago, I forgot. Okay, so therefore we got 1 over y squared equals to 1 plus c e to the x squared. And so it's not too much trouble. I'll find the explicit solution here. Y squared equals to 1 over 1 plus c e to the x squared. Therefore, y is apparently plus or minus 1 over the square root of 1 plus c e to the x squared. And you choose the plus or minus depending on initial conditions. Yep.
Is there only one way of doing these? Because it seems like separation of variables would work as well. You just bring the negative 2x to the other side and separate the negative 2x.
Let's see here. Here you're like separation of variables. Yeah, fair enough. We could have done separation of variables here. That might have been faster.
So there's not just one method for each variable?
No.
Different methods.
No, these methods are not mutually exclusive. There are often several methods that'll work, yeah. And I think I like your way of doing this one better, actually. Like separation of variables would be faster, yeah.
I worked it out and it was quite simple.
Good, good. At the same time, I know in my heart you guys need more practice with integrating factor methods, so I have no regrets. But yes, thank you. Very, very good comment. Okay, what's my next thing here? Yes. Example 4. Where was my... Of course, you know, substitution problems are nice in the sense that they give us, you know, further experience with the things I gave you a couple of examples of last time, right? I mean, it always goes back to those basic 3 techniques, I think. That's always is probably definitely, not possibly, but certainly too strong a statement. There's a lot out there in differential equations. We just show you kind of some things which are known and are not too hard to understand in the introductory course, yeah. But on the other hand, God has been kind to us. For the most part, all of the interesting applications in physics are amenable to the solution techniques I show you. So that is a very fortunate thing. In fact, it's such a damning indictment on naturalistic philosophy. It's driven them to suggest the existence of multiple universes and things. The idea that we can solve the equations of physics meaningfully and understand them, it's very perplexing to people who don't believe in God. I think it was Einstein who said the greatest mystery is why there is physical law at all. Anyway, I digress. Okay, so here's another one. This one is like, wait a minute. Well, this one's not like the others, right? This one doesn't belong. Let's see here. I don't know, nobody watches Sesame Street anymore. I know I'm referencing things that are only on paid cable channels. So y prime prime plus y prime equals x squared. This is second order, right? But this one, if we we can do what's called reduction of order, all right? Reduction of order is an important technique. And here, basically, we just say, okay, what we're going to do is v equal to y prime, right? If v is equal to y prime, what's v prime equal to? Y prime prime, yeah? So what's the differential equation become after we make this reduction of order? And you'll see why it's called reduction of order pretty quickly, right? Duh. So it becomes v prime, right, plus v equal to x squared. Now this, we can go back and use that sort of meta example I did last time where we like here, you could think of r equals to 1 and g equals to x squared in the example we did last class. I'll just write down the integrating factor here. The integrating factor is e to the x. Ooh, ouch. Well, fine. I mean, we can integrate x squared times e to the x. It just isn't, you know, entirely obvious, I guess. Oops, no integration yet, right? Here I'm just doing a reverse product rule. This time, Nathan, I think that we can't do separation of variables because the v and the x are, yeah, they're not really in any way intertwined. Sorry. Let's see here. Not an actual word. Yet students understand. Let's see here. Equals to the integral of x squared e to the x dx. This looks like a job for integration by parts. Here's our u. Here's our, I guess I'll say dw. So that gives me x squared e to the x minus the integral of 2x e to the x dx. Again, I'll make that my dw prime, well, dw2 or something. And this will be my u2. I get x squared e to the x minus 2x e to the x plus the integral of 2 e to the x dx, I believe. And so we get x squared e to the x minus 2x e to the x plus 2 e to the x, all right, plus a constant. So well, that was unpleasant. Why did I do that? Anyway, what was v? I forgot already. Oh, v was dy dx. Oh, man, look at that. So we got dy dx, right? So you notice that there's an e to the x almost everywhere here, right? You have e to the x here, 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 just not there. So we can divide by e to the x, and when we do that, that brings us to dy dx equals to what? I take it back. It's not too bad. I thought in the next step I was going to have to integrate like x squared e to the x and x e to the x and e to the x all at once, but no. That's not what happens. See, because dividing by e to the x removes the e to the x, and we just get dy dx equals to this, which is harmless, right? This differential equation, you didn't need my course or this course to solve, right? We could have solved this in Calc 2. Just integrate both sides, right? What's y equal to? One third x cubed minus x squared plus 2x, right? Minus c e to the minus x. There you go. Oh, plus c2, right? Because we integrated. Like I told you yesterday, if we solve a second order problem and find the general solution, we kind of expect that there are going to be two parameters in the solution, in this case c and c2. Does this make sense? So the reduction of order is a technique we can use to take a second order problem and convert it into like a pair of stacked first order problems. Like we do the reduction of order and, you know, this happens. Now, here, what would happen if we tried to do reduction of order? You remember last time? And any questions about this before all right. So last time I showed you that y prime prime plus y equals to 0. Well, I didn't really show you. I claimed that this had solutions, c1 cosine x plus c2 sine x as a solution. Now, it's pretty easy for you to, and this is something that I failed to say yesterday. What is a solution to a differential equation? For shame, I didn't say this yesterday. Hey, wait a minute, shame on you for not asking. I said our goal is to find a solution, a natural question that you should ask as a student, a person who's curious and trying to learn things. What is a solution? What do you mean? Well, we know what solutions are to algebraic equations, right? Like if I have x squared, minus 3x plus 2 equal to 0, you know what we do, right? And then that makes it clear that if you give me x equals to 2, or if you give me x equals to 1, those are solutions, right? What does that mean, though? X equals 1 and x equals 2 are solutions. Graphically, they're x-intercepts. If we look at y equals to x squared minus 3x plus 2, that's true. That's true. But more directly, just in terms of the equation itself, what does it mean about to say something's a solution to an equation? It means that if we plug it in, right, the equation's true. Like 5 is not a solution because 25 minus 3 times 5 plus 2 is equal to what? 12, right? Which is not equal to 0. So consequently, 5 is not a solution, right? This differential equation, right? If I say y equals to e to the x, you can easily calculate that y prime prime is still e to the x. So when I take y prime prime plus y, I get 2e to the x, which of course is not equal to 0. So e to the x is not a solution to y prime prime plus y equal to 0. In contrast, cosine and sine are solutions. What happens when you differentiate cosine 2 times? Yeah, think about it. It goes back to minus cosine, right? And the same for sine. Sine differentiates to cosine. Cosine differentiates back to minus sine. So if you look at y prime prime plus y, it's equal to 0 if you set y equal to cosine, or if you set y equal to sine. And because of the structure of this differential equation, if you take any linear combination, right, this is a linear combination right here. This is called a linear combination of sine and cosine, all right? You can see that because the second derivative is linear, because it's just the first derivative done 2 times, and the first derivative is a linear thing, right? You pull constants out, you break up cross addition. It follows that linear combination of sine and cosines is also a solution. This is a signature of what's called a homogeneous differential equation. This is the other kind of homogeneous differential equation. Different use of the term than that one. Sorry about that. So my question then is, can we derive this? Like, I showed you it works, right? But that would be sort of like I ask you to integrate secant x. And I tell you, oh, integral of secant x is easy. It's the natural log of the secant plus the tangent, absolute value. And you would then ask, that's not a method to derive it, right? You just told me the answer, right? So in the same sense, I just told you the answer to this. Could we derive it from reduction of order? What do you think? Let's try. What happens if we try to do reduction of order on y prime prime? If you don't mind, I'm going to erase the previous problem here. And let's just do y prime prime, get rid of the x squared. No reason to make it too much trouble. Y prime prime plus y equal to 0. Let us attempt reduction of order here, see what happens to us. So this will become what? This becomes, I don't know. So that becomes v prime plus y equal to 0, right? That's kind of no fun. That's dv dx plus y equals to 0, right? But that's not the kind of thing I want, right? I want just v and x left over, right? I don't want a vx and a y. Maybe I can trade the x for a y somehow. Maybe it makes sense to do, let's see here. Trying to think of how to, what if I say dy dx, no, dx dy, dv dx plus dx dy, y equals to 0. Then we could think of like a chain rule, basically. This would give us dv dy equal to, dv dy equal, oh, but that's still, no, I still got x prime. Man, how do I do this one? I forgot. I'd forgotten about this example. We were, my wife found out about, like, there's some kind of free thing going on at Chick-fil-A on Tuesdays in June. If you go, you can get like a free entree if you buy a drink or something. But then I was like, I don't want to wait. There's like hundreds of people. It's just, there's a lot of people there. And like the whole purpose of going to breakfast is to eat with my family. So if they're going to eat in the car, so I just went to Panera, which is, where'd my notes go? So I wrote my notes on the napkin, and then I was looking at my notes. I stumbled upon this. This is example 2.4.11, where I actually derive the sine and cosine using reduction of order. But there must be some sneaky step in there because, you know, well, I'm stuck. Can you see a way around that? I'm really curious to see what I did. Let's see what kind of sneaky step I did. And then we are going to take a well-deserved break. Although I do need to look at the other example. I got the projector out. Let's hear. Come on. Come on. Is it, sometimes they, oh, must be I've got the wrong source. Ah, there we go. Let me get out my laser. Oh, what? Hey, it's not cool. Don't do that. All right. So here it is. Y prime prime plus y equal to 0. So, oh, and I've got t instead of x. That's not a big deal, right? Oh, I use a rather different technique this time. I don't use reduction of order. I use the v/dv/dx trick, which I'll talk more about after the break. But basically, when you've got acceleration, you can rewrite it as velocity times the derivative of the velocity with respect to position, which I usually refer to as the v/dv/dx trick, because I'm usually working with x as position, and it's more fun to say v/dv/dx. We'll do it again after break, but this is a sneaky substitution. See, I trade dv dt for dy dt times dv dy. This is the chain rule. This makes sense for one-dimensional motion, but that's v, dv dy. So with this substitution, I trade my second derivative in time for a first derivative in position. And after doing that, I've got a first order problem, which is in fact exact, right? It's exact because the level function is 1/2 v squared plus 1/2 y squared. And so v is equal to plus or minus the square root of 1 minus y squared, but remember v is dy dt, so we get this, and then the integral of that is inverse sine of y over c. Is plus or minus t, but then if we take the sine of both sides, we get y is equal to c plus or minus t plus a phase angle. Now, trigonometry can produce sine or cosine from this upon appropriate choice of plus, minus, and phi. And so this is a straight up derivation of the sine cosine solution I pulled from the thin air last time, right? So this is a little bit disturbing from the perspective of, I then ask you the question, so suppose you want to solve y prime prime plus 2y prime plus 3y equals to 0. How would you solve it? How would you solve that differential equation? Using our current techniques, it would be some sort of amalgam of reduction of order and this VdVdx trick, right? You have to integrate 2 times. It's quite awful. But by the end of today, I'll probably show you that we can solve this with almost no effort. So it turns out this deriving way of thing, I mean, it's fine to derive things once or twice, right? But there are better techniques to solve this problem, which I'll show you. Now let me just jump back in those just real brief, and then we'll take a break. Which one did I say it was? 2.43 was it? Let's see here. What did I do different? I made some stupid sign error somewhere. So this was, when I solved for dy dx, v plus x dv dx, I got that the same. 1 plus v over v, oh, right there. See that? V minus 1? It was, no, it's v minus 1. Oh, that wasn't it. Dang it. Where is the mistake? That one was the same. Well, this is very embarrassing. I already fixed this problem. Stink. And so this, you know what I did here was I've done a little bit more work here. What it is, I multiply both sides by minus 2. That gives us what? Multiplying by minus 2 brings this to 1 over x squared. And so you've got this, when you take the exponential of both sides, you get a constant over x squared from this. And this is, y squared over x squared minus 2y over x minus x. And so after you multiply through by x squared, it gives you that. So it's just a little bit of algebra to get from here to there. Oh man, actually this example is fine. I used to have a mistake here. I obviously fixed it and forgot I fixed it and remembered the mistake because, well, math guilt, I guess. All right, guys, let's take a 10-minute break, and then we'll start again with applications, all right? So we'll start again at 11:53. Well, 54, 11:54. Is my clock right?